Alright, this video is for Unit 2 EOC review. This is biochemistry, and this has been historically not only for you all, but for previous generations of my class, which has only been 3 years. This has been a difficult unit, and I think it's largely because we haven't had a lot of exposure to chemistry up to this point, and it is kind of daunting, and so we're going to get straight to it. The basics here, just please don't mess up on these basics. When you're talking about an atom, you're talking about just a couple of things. You're talking about, well, actually, let me read. Atoms have things called protons in them, and protons are positively charged. Well, they also have particles called neutrons in them. Neutrons are neutral. They have no charge. They're not neutrally charged. They have no charge. And swarming around the outside are these electrons, and they swarm around out here in something called the electron cloud. And so we kind of have an idea of where they might be, but because they're always moving, we just place them in this cloud. And when you have chemistry, you'll learn more about the way that they run around and orbit things. But for now, we're going to keep it very simple. Now, the electrons, again, negative charge, protons, positive charge, and neutrons have no charge. Now, there's several numbers associated with atoms, so let's get those. There is the atomic number, and the atomic number is the number of protons. When you look up on the board and you see something that looks like this, and you see, in this case, this is helium, and up here in this upper right hand corner you'll see a nice number like that. That number tells you how many protons it has. This is what makes an element an element. Well, what is an element? An element is a substance that is composed of one type of atom. Substance that is composed of one type of atom. So when I have helium, I have just helium atoms. All right, if I have something else in there, I have a mixture of things. Like when we go outside and breathe our air, that is a mixture of things. Helium is just helium, and helium has 2 protons. If you put 3 protons in it, it's no longer helium, it becomes lithium. Now, down at the bottom, you have another number, and this other number down here, and let me 4.0 something something, is called the mass number. Mass number, or the atomic mass, you'll sometimes see it called. And this is the mass of the atom. And typically, this is the number of protons plus the number of neutrons. And you'll see some of these tiny decimals because it's also giving you the mass of electrons, which is very small. So neutrons plus protons. And you can usually guess how many neutrons an atom has just by simply subtracting the number of protons that are in it. So for instance, in helium, when you look at the periodic table, you see a 4 there. Well, you subtract the 2 from it, and you can say, well, helium has 2 neutrons. Very easy to figure out. Now, sometimes there are isotopes. Now, what is an isotope? An isotope is a variation of that element in which the atom itself has more neutrons than atoms, the normal atoms of that element. So we'll take something like carbon, 1, 2, 3, 4, 5, 6, and in carbon there are also normally 1, 2, 3, 4, 5, 6 neutrons, and of course floating around there are 1, 2, 3, 4, 5, 6 electrons. And this is your normal carbon atom. Well, a carbon atom that has 8 neutrons is called carbon 14. because now the new mass number, instead of 12, is now 14, because there are 8 neutrons. And so these isotopes differ in neutrons only. Isotopes are sometimes unstable, like carbon-14, and these lead to radioactive decay. And this rate of decay is actually constant. And so these sorts of materials can be used to date older material, such as carbon-14. It is used to date organic material because there is a certain amount of carbon-14 in everything, and it decays over time, and it's a regular rate. So scientists can use that to measure the approximate age of something that they find, an animal or a person or whatever. Well, electrons bring a little bit more to the table. Let me just use my carbon atom here as an example. And so for electrons, these electrons have a regular way about them as far as a regular order to them. And there are several shells of electrons, like I was talking about earlier. And so you have a nucleus here in the middle, as you see. And then you have several shells of electrons, and those shells of electrons go from inside to outside. And as you get further outside, the electrons are going to be spinning at different speeds. The closer to the middle, they're spinning really fast. The further outside, they're spinning a little slower. And those outside electrons are called valence electrons. Now, what do you suppose is going to happen if those electrons get to spinning really fast? Well, it's very similar to like tying something to a rope and spinning around your head. Eventually, it would get so fast that you could no longer hold on to it, and it would just kind of spin out into nowhere. Whereas if you were trying to spin it real slow, it would eventually get so slow that it would collapse in on you. Well, it's very similar to an atom. An atom that has lots and lots of energy, those electrons will spin and will make the atom actually a lot bigger. It'll kind of expand as those electrons are spinning. Whereas if there's not very much energy, the electrons are going to be closer to the nucleus. Okay? And an atom that loses electrons very readily or gains an electron readily is called an ion. And so an ion is actually a charged atom. A charged atom. And ones that you'll see very regularly are things like sodium and chloride. Sodium loves to get rid of its outside electron. It has one electron in its outer shell, and when it gets any amount of energy, that electron will just readily go away. Well, sodium normally has 11 protons and 11 electrons. 11 pluses, 11 minuses, so a net charge of 0. Well, what happens if that outside electron goes away? Then you have 10. And so what becomes the new charge of this sodium? Plus 1. And now it's an ion. It is now charged, and so we will typically write ions like so. Well, chlorine is different. Chlorine has 17 protons, 17 electrons, and chlorine will readily accept an electron. And so it will readily gain another electron, causing it to have a -1 charge. And like you've learned, these opposites attract one another, and they can actually form bonds with one another. Now, positive ions are called cations. I mean, this is kind of the way I remember it. Just think of cats, and cats are positive things if you like them. Whereas anions, if your handwriting is bad like mine, it kind of looks like onion. And maybe you don't like onions and you think they're negative. I don't know. Maybe that helps. Maybe it doesn't. But cations are positive and anions are negative. A couple other terms. The term molecule. A molecule is formed when two atoms join together chemically. O2 is an example of a molecule. H2O is an example of a molecule. I don't know why I put that 2 up there. All right. Compounds are formed when two different atoms, at least two different atoms, join together. So O2 is not a compound because it's the same atom, but H2O qualifies as a molecule and a compound in this case. Now a little bit more, just a few terms that you should be familiar with. Well, first of all, let's talk about chemical bonds and this idea of kinetic and potential energy. Energy is stored up in chemical bonds, and so when bonds are broken, that energy is released. And so when you have a molecule like H2O, here's your O, there's your little H's, and these are chemical bonds, and inside those chemical bonds are lots and lots of energy. Well, when you break those bonds, all of that energy is released. And so that is called kinetic energy. Kinetic energy. So if you break a bond, energy is released, then what is needed to put that bond back together? You need energy. And when you put energy back into that bond, that energy is now potential energy. It has the potential to do something. And so chemical bonds, depending on their strength, have differing amounts of energy. And so we'll list the types of chemical bonds from strongest to weakest. First, there are covalent bonds. And covalent bonds are the share when two atoms share electrons. This is when they are sharing electrons in those outer shells. Actually, when water's a good example of this. Water has 10 electrons, and a good way of thinking about this, they just kind of circle around the entire thing. They're sharing the 2 from hydrogen and the 8 from oxygen, and they're just sharing all of those electrons. All right. Whereas the next strongest type of bond, an ionic bond, there is no sharing, but there is transferring of electrons. And so this has to do with those ions that we talked about earlier, like sodium, which loves to get rid of an electron, and chlorine, which loves to grab an electron. So you can imagine our little electron friend here. He stays with chlorine sometimes, but chlorine gives him up. And there's just this constant transferring back and forth of these electrons. So this relationship creates a bond between sodium and chloride, but that bond can be broken in the right situation. And that's why, salt, for instance, forms crystals because of these very structured bonds. But it's also why salt dissolves in water, because water will kind of easily break those ionic bonds apart and cause them to just be separate ions. Which kind of brings us to our next subject here is hydrogen bonds. And a hydrogen bond is a magnetic attraction between two polar molecules. So this has to do with polar molecules. We're going to talk about polarity of water in a little bit in another video. But this is usually between a hydrogen of one atom and an oxygen or a nitrogen of another atom. So let's just do our water here, and well, here's another water over here. There's a magnetic attraction between that oxygen and that hydrogen there, and that is a hydrogen bond. It is a bond that is very important in nature, probably the most important bond in living systems. However, it doesn't require a lot of energy to break, and so this is why your body uses this in areas that have to be broken apart pretty regularly, because it doesn't require a lot of energy, but it's also stable enough to keep two things together. And lastly, are bonds called van der Waals forces. And van der Waals forces are just slight attractions between oppositely charged regions of large molecules. So let me give you an example of this. Say we have two large molecules, two big proteins here. And a protein could be thousands of atoms in there. Well, when these two molecules get close to one another, we can't get them close to one another. When these two molecules get close to one another, opposites attract. And so what we would expect to happen is all the electrons would come on this one. Well, that's going to cause the electrons on this one to go to the other side, and there's going to be a more positive charge here and a more negative charge here. And so those two big atoms are temporarily attracted to one another. You see this is important in temporary bonding between enzymes and substrates, which we'll talk about momentarily. And these are the weakest interactions between two molecules.